You are listening to AI Paper Swap, and today we are unpacking the paper Scaling Behavior Foundation Model for Humanoid Robots. And I'm giving you the core insight right now, straight up. To build a general-purpose humanoid controller, scaling isn't just about, throwing more data at a neural network. This paper proves that effective scaling requires coordinating three very distinct pillars.
Right. It's a very specific recipe.
Exactly. Pillar 1 is a learning paradigm based on motion tracking in the global frame. Pillar 2 is a strategic balance in your behavioral data, meaning you scale on policy rollouts for quantity, but you expand reference motions for diversity. And Pillar 3 is an expressive humanoid transformer architecture.
And for anyone working in embodied AI right now, the headline result of coordinating those three things is just staggering.
Yeah.
By integrating that global tracking, the balanced data, and this transformer architecture, they reduced mean per key point position error by over 10% in local mode.
Which is solid on its own.
Yeah, but then there's a massive 82% drop in global mode compared to existing state-of-the-art controllers.
An 82% drop in global error. I mean, that is not an incremental update. That is a fundamental leap in how these machines operate.
Totally.
But to understand how they got there, we have to look closely at the math behind how they framed the learning objective in the first place.
Right, because they formulated humanoid control as a Markov decision process.
Yeah, an MDP. Optimized through PPO, proximal policy optimization. Now, PPO is pretty standard in reinforcement learning, but the critical shift here is the reward function itself.
Which is where Pillar 1 comes in.
Exactly. They explicitly demanded that the robot reproduce integrated whole-body behaviors in the global frame, not just doing local pose tracking that, completely ignores where the robot's center of mass is actually traveling in the room.
Yeah, it completely changes how we define success for the algorithm. Because historically, a lot of mimic-based approaches in continuous control, they decouple the global root evolution from the local pose tracking.
Which causes problems.
Huge problems.
Yeah.
They essentially tell the algorithm, hey, make the joints look like this reference motion and just don't worry about where the robot is physically located.
Right.
But when you do that, you introduce a massive issue of behavioral ambiguity.
Yeah, and the best way I can think to describe this local tracking ambiguity to you is to imagine someone moonwalking on a treadmill.
Oh, that's a perfect analogy.
Right, because if you are only looking at the local joint angles, like the hips swinging, the knees bending, the pose tracking looks flawless, the math tells the policy, great job, you're walking forward.
But in the global frame, the robot hasn't moved an inch.
Exactly, it's stationary. So by forcing the tracking into the global frame, you strip away that mathematical illusion. You force the robot to actually conquer physical space. You just can't fake walking forward by sliding your feet on the floor.
Yeah, and if you're an RL engineer listening right now, think about what this means for your gradients. When you decouple root evolution from pose tracking, errors in the root motion don't penalize the pose tracking.
But physics doesn't work like that.
Right. Physics doesn't decouple.
Ah.
If your center of mass is slightly off by 2 centimeters, your next footstep physically has to change to compensate, or the robot just falls over.
Right.
So by enforcing strict global tracking, any error in the root motion mathematically propagates to the whole body in your reward signal.
So you're basically creating a much denser, far less forgiving reward landscape.
Exactly. The policy can no longer cheat the math. If it wants to minimize the loss, it is forced to achieve true behavioral mastery of the physics. It has to understand momentum, gravity, friction.
And what's brilliant is that doing this doesn't trap the model into only doing global navigation.
No.
Because they trained this behavior foundation model, or BFM, to master the harsh realities of global physics, you can use the exact same model for both global control, like navigating to a GPS coordinate, and local control.
Right, you just re-anchor the command signals to the robot's current root state at inference time.
Yeah, the BFM supports both seamlessly because it actually understands the underlying physics of movement now, not just, joint mimicry.
But building that dense reward landscape creates a massive computational challenge.
Oh, sure.
Because once you establish a strict global reward signal, your PPO algorithm needs an enormous amount of varied experience to actually learn it without falling into local minima.
Right.
And in a PPO framework, data scaling operates entirely differently than it does in supervised learning. You can't just scrape the internet for a static data set, feed it to the model, and expect it to scale.
Right. So let's dive into the data set they built, because the scale here is wild. They curated 102 million frames of human motion at 50 frames per second.
Massive.
Yeah, and they pulled from highly specific sources. Roughly 47% is from Bone Seed, which focuses on whole body interactions. About 30% is from Embody 3D.
Yeah, and they mixed in datasets like AMAS, Grab, Fine Bands.
Homo, yeah. So you have everything from basic walking to highly complex object manipulation and even dancing. But the paper clarifies a huge misconception that I think trips up a lot of teams.
Oh, the quantity versus diversity thing.
Exactly. Just adding more reference motions to this massive data set isn't actually scaling data in the context of PPO.
Yeah, this is where so many scaling efforts in robotics just hit a wall. In PPO, your actual data quantity, the physical experiences your network uses to update its policy gradients, that comes entirely from on-policy rollout.
Right, the simulation itself.
Exactly. Your algorithm is physically simulating the robot, trying to do the task, failing, and trying again. So if you want more data quantity, you have to increase your parallel GPUs and extend your rollout horizons to simulator.
That's your volume.
Right. That is your volume. Those 102 million frames of reference motions, they don't provide volume. They provide diversity. They act as the targets that shape the distribution of the behaviors your robot attempts to imitate.
Okay, wait, let me push back on this for a second. Because standard machine learning logic dictates that more compute generally equals better performance.
Usually, yeah.
So if I'm an ML engineer and I suddenly get the budget to buy 10,000 more GPUs, shouldn't my robot naturally get more capable? Because I'm generating exponentially more on-policy data.
You would think so, right. But that is exactly the trap the authors highlight here.
Okay, why?
If you scale your compute, meaning you massively scale your on-policy rollouts without simultaneously scaling the diversity of your reference motions, you experience severe diminishing returns. The authors call this homogeneous scaling.
Homogeneous scaling, okay.
Yeah, let's say your reference data is mostly just basic walking and running.
Yeah.
If you throw 10,000 GPUs at that, your policy just becomes incredibly perfectly robust at basic walking and running.
So you're just hardening the policy against the few behaviors it already knows.
Exactly.
It's like going to the gym for 10 hours a day, but the only exercise you ever do is a bicep curl.
That's a great way to look at it.
You're going to have amazing biceps, but you won't be a functional athlete. The compute gives you the repetitions, but the reference data is the coach giving you a diverse curriculum.
Precisely. To get a real performance leap, you need heterogeneous scaling. You must introduce novel behaviors alongside that massive compute.
Which is why the dancing data or the manipulation data is so critical.
Yeah. A robot needs to understand the extreme edges of its joint limits like it experiences when dancing, so that when it trips in the real world, it knows how to dynamically recover its balance, instead of just rigidly trying to execute a walking cycle while falling over.
Right. You need the absolute synergy of rollout quantity and reference diversity.
Yes.
But practically speaking, simulating 102 million frames of diverse, complex behaviors across thousands of GPUs sounds wildly inefficient if the robot keeps failing.
It can be.
Like if a simulated robot is trying to learn a backflip and it falls on its face at frame 10 out of 200, isn't the algorithm wasting massive amounts of compute just simulating the robot flailing on the floor for the next 190 frames?
Yes. And worse than wasting compute, it actually destroys the learning process.
How so?
Well, if the robot is on the floor, flailing, while the reference motion is midair finishing a backflip, the mathematical error between those two states is astronomical.
Oh, right.
And PPO tries to minimize this error, but the gradients become absolute garbage noise because the robot's physical state is entirely detached from the reference state.
So what's the fix?
To solve this, the authors implemented early termination. The exact moment any link on the humanoid deviates by more than half a meter in the global frame, the simulation episode ends immediately.
Oh, wow. So they just cut the garbage gradients off before they infect the policy.
Exactly.
But doesn't that create a new problem? I mean, if you cut the episode at frame 10 and just restart from the beginning of the motion every single time, the robot is going to get really, really good at the first 10 frames of the backflip, but it'll literally never see the middle of the motion.
Right. And that is where reference state initialization comes in, RSI.
Okay, RSI.
Instead of starting from frame 0, the system reinitializes the humanoid right next to the termination point.
Mm-hmm.
They place the robot back onto the desired trajectory manifold, physically matching the reference state at the exact moment it failed, and let it try again from there.
Oh, that's brilliant. It's exactly like a video game checkpoint just before a boss fight.
Yes.
You don't have to play the entire 3-hour level again just to get one attempt at the boss. You just keep practicing the exact sequence where you keep dying until you master it.
Exactly. And they pair that checkpointing system with something called hard mining.
Hard mining.
Yeah. If a specific reference trajectory keeps failing, say, a really complex pirouette, they dynamically update the sampling weights. They mathematically force the PPO algorithm to resample those high-loss, failed trajectories more frequently.
Oh, so it can't ignore the hard stuff.
Exactly. Instead of the algorithm just averaging out its loss by practicing the easy walking motions it already knows, hard mining forces the model to constantly confront and learn the most difficult physical motions in the dataset.
Man, it just creates this relentless, closed loop of evaluation, failure, targeted feedback, and resampling.
It's intense.
But to actually digest the strict global frame tracking, the massive heterogeneous data scaling, the continuous hard mining updates, you need an architecture that doesn't buckle under all that complexity.
Right.
And traditionally, in reinforcement learning for continuous control, everyone just defaults to MLPs, right? Multi-layer perceptrons. Because they're fast, they're mathematically well understood, they get the job done.
Well, they get the job done for simple, constrained environments.
Right.
But MLPs utilize fixed-size weight matrices.
Right.
When you are trying to ingest 102 million frames of highly diverse multimodal behaviors, MLPs just hit a hard capacity wall.
They just can't route the data.
Right. They physically cannot dynamically route that much contextual information. So the authors made a crucial architectural leap here. They shifted to the humanoid transformer.
Okay, let's unpack this for the technical folks listening. Moving to a transformer for low-level continuous physical control is a massive paradigm shift. Because transformers are famous for processing text, not torque, how does this actually work mechanically inside the robot's control loop?
Okay, so they designed the architecture to split the cognitive load. First, it uses self-attention to process the historical context of the robot's own body.
Okay.
Physically, the self-attention mechanism is constantly asking, where were my left ankle and right hip over the last few fractions of a second, and what is my current physical momentum?
So it builds an internal model of itself.
Exactly, a dynamic internal representation of its own physical state. Then it uses cross-attention to process the future goal sequences.
Got it. So the cross-attention is looking ahead at the reference trajectory.
Yes. The cross-attention allows the network to constantly condition its current physical action on the upcoming behavioral specifications.
Okay.
It asks, given my current momentum that I learned from self-attention, how do I need to actuate my motors right this millisecond to map onto the poses I need to hit 1 second from now?
That is so elegant. And because it uses this attention mechanism, they were able to build the model to support incredibly diverse control modes.
Yeah, the flexibility is crazy.
You have whole body mode, root and hand mode, root and end effector mode. You can command this robot by giving it the exact joint angles for all 20 plus joints, or you can literally just give it a 3D coordinate and say, hey, put your right hand here and keep your root over there.
And the transformer just fills in the rest of the body kinematics dynamically.
It's wild. But here is the part of the paper that absolutely blew my mind. The emergent latent space.
Oh, yeah. This is, without a doubt, the most profound scientific finding in the entire study.
I mean, to set the stage for why this is so crazy for you listening, the researchers did not explicitly code any auxiliary objectives to force the model to organize its behaviors.
None.
They didn't write a script saying, cluster all the walking motions in this part of the network and cluster all the grasping motions over there. They just gave it the global tracking loss we talked about earlier. Right. But naturally, completely on its own, a highly structured latent space emerged inside the transformer.
It organized itself.
Yeah. I look at this and I immediately compare it to large language models. When you train an LLM to just predict the next word on a massive corpus of text, it suddenly learns grammar, syntax, and logic without ever being explicitly taught the rules of English.
Yes. The parallels to emergent behaviors in LLMs are undeniable here.
Because here, the humanoid transformer is just trying to predict the next physical motor action to minimize tracking loss, and in the process, it just figures out the underlying physics of our universe.
Exactly. And when the authors mapped out this emergent latent space, this high-dimensional hypersphere inside the model's weights, they found two critical properties that prove it learned physics, and not just mimicry.
Okay, what's the first one?
First is local continuity. If you mathematically move a vector slightly within this latent space, the resulting physical motions of the robot transition smoothly.
So no sudden glitches.
Right, there's no jitter. It doesn't suddenly snap from a smooth forward walk into a violent, glitched-out flail. The space is continuous, just like physical reality.
Wow. And the second property is the global organization, right? Like distinct behavioral intentions occupy distinguishable logical regions.
Exactly. The representations actually preserve directional relationships.
How so?
Well, the cluster of latent vectors for walking forward and the cluster for walking backward, they end up structurally organized in ways that are spatially logical relative to each other. The model essentially built its own internal mathematical map of physical kinematics.
That is fascinating, and it is incredibly robust, too. I want to talk about the noise injection tests they ran, because some people listening might be thinking, well, maybe it just memorized the 102 million frames like a giant lookup table.
And that is the exact skepticism you should have.
Right.
To test whether it generalized or just memorized, the authors intentionally injected noise directly into the latent space. They took the latent vectors representing specific command trajectories and mathematically rotated them, pushing them far away from their exact coordinates.
So if it was a lookup table, it would break.
Exactly, because the exact coordinate is gone. But despite this noise, the model still executed the intended behaviors flawlessly.
Which proves generalization.
Definitively. It proves the network has abstracted the underlying physical concepts of the movement, like balance and momentum, rather than just memorizing a numerical sequence from a specific demonstration.
And there's one more piece to this architecture pillar that ties it all together. As they scaled the model capacity up, pushing the humanoid transformer to almost 12 million parameters, 11.9 million to be exact, they noticed something really fascinating about how it handles those different control modes we talked about earlier.
Oh, the convergence.
Yeah, the representations across the different modes actually started to converge in the latent space.
Right, and this is the ultimate proof of extraction. Whether you command the robot using a highly detailed whole-body pose, or if you just use root and hand mode to give it a sparse endpoint, the large-scale transformer maps those two completely different mathematical inputs into the exact same region of the latent space for the same underlying action.
That is so cool.
It knows that reaching for a cup is fundamentally the same physical concept, regardless of how you format the instruction. It has achieved a universal, abstracted understanding of behavior.
So zooming out, what does this all mean for the big picture? We're constantly hearing about the quest for general-purpose embodied agents, right? Humanoid robots that can actually operate in our homes, our factories, our messy, unstructured human environments.
It means we finally have a mathematically principled, scalable path forward for low-level control.
Yeah.
The final result, that 82% drop in global mean per key point position error, isn't just a better score on a leaderboard. It represents a total paradigm shift in control fidelity. By meticulously coordinating global frame tracking to force physical interaction, balancing rollout quantity with reference diversity to prevent homogeneous stagnation, and leveraging the immense routing capacity of transformers, this paper proves that behavior foundation models are the correct architectural foundation for humanoids.
Yeah, they've effectively built an incredibly robust, highly capable spinal cord and cerebellum for the robot. It has achieved low-level physical mastery. It knows how to balance, how to recover from a trip, how to move its mass through space without falling over, practically no matter what you ask it to do physically.
But this raises a really fascinating question, and it's something the authors touch on in their discussion section, which I think is a perfect frontier for us to consider.
Okay, let's hear it.
We now have this incredibly capable behavior foundation model. It can take diverse, low-level control modes and turn them into flawless, continuous physical execution. But a robot in a home needs high-level semantic reasoning.
Right.
It needs a vision language model, a VLM, acting as its brain.
Right, you have the cerebellum, but how do you connect it to the prefrontal cortex?
Exactly. The VLM can look at a messy kitchen counter and reason, hey, I need to put the milk in the fridge before it spoils. But what is the optimal connective tissue between that semantic reasoning and this BFM?
That's a huge question.
How exactly should the VLM talk to it? Should the VLM output precise 3D hand coordinates for the BFM to track? Should it output latent vectors directly into the transformer? Or should it output natural language that another intermediate layer translates into root trajectories?
Yeah, that is the next great challenge for AI researchers listening right now. The physical foundation is built, the math works, but designing that connective tissue between high-level semantic reasoning and this beautiful emergent physical mastery, That is where the field goes next.
Absolutely.
Because once you bridge that gap seamlessly, that mathematical treadmill the robot was moonwalking on, it disappears entirely, and the robot finally steps out into the real world.